Hi everybody, good morning. It's a bit loud. Okay, my name's Ron Tow, I'm from the UK, and I'm here today to talk to you about Wi-Fi. I'm sure you're all aware that MikroTik has a product called CAPsMAN, and it's very, very easy and quick to set up. In fact, it does sound a bit complicated when you're first playing with it. It does seem a little bit complicated, but actually it's a very, very simple controller for Wi-Fi. But if you don't actually understand how the underlying fundamental Wi-Fi protocol, the A2.2.11 protocol functions, we're going to have all kinds of major issues and problems. So I'm going to have a little talk about that this morning. So what's my background and why am I in a position to have any kind of authority on this subject? I was supposed to have gone into the Navy as a wireless operator and electronics repair officer, working on marine electronics and marine radar. So 3 gigs and 9 gig radar for the Navy. But it was the late 1970s, and in the merchant Navy at that time, we had an oil crisis, one of many at that time, and it meant that a lot of vessels were being moored up in Norwegian fjords. There were no oil tankers, there was hardly any freighting going on around the world, and they just didn't need radio and electronics officers. So I was out of a job. As soon as I left college, I was out of a job. Nothing to go to. So I joined the government. Ended up getting recruited, as it turned out, and worked for the government and spent really the next 30 years playing with RF and playing with devices. So I'd learnt all the theory whilst I was at college, and then I really genuinely learnt the practical side of how the laws of physics and RF actually worked in the real workplace and in a more fun way. It was a good 30 years of my life and really enjoyed it very much indeed and learnt a hell of a lot from other people. So I was around at the time of the birth of Wi-Fi when Alvarian, or BreezeCom as it was then, was around and started making very, very early chipsets and Wi-Fi bridging devices. And then around in the early 2000s, we started to see in the UK wireless ISPs starting to set up using devices that were commercially available for the home, but then placing them into waterproof Tupperware boxes and mounting them on rooftops and making meshed networks and the beginnings of open mesh as well, for example. And that was all on 2.4 gigs. So they were doing point-to-point connections across the country on 2.4, delivery of Wi-Fi into the home on 2.4. Interference was hell. There was a lot of interference. And they were putting linear amplifiers because the links weren't going long enough distances and they couldn't get large enough antennas. So they were putting 1-watt amplifiers onto the outputs. And it was generating crap across the entire 2.4 gigahertz band. In the UK, those other organizations that have radio spectrum on either side of the 2.4 gigahertz band were also starting to get lots of interference from the users of the 2.4 gig free unlicensed band. One of those organizations is the police. You may have seen those wonderful videos on the TV where you get the heli-telly. The helicopter is chasing the cars and the good guys are chasing the bad guys until somebody then says it's crash, 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 and they then get the people running out of the cars and chasing them with dogs. Well, that helicopter with the camera, with the massive zoom lens on it, is actually downlinked from the helicopter to the ground on 2.4 gigs, or very, very near to it. And of course, they're just getting wiped out. Picture would break up. It was all analog. Anybody could set up a receiver at home, which was fun because it meant you could actually watch the heli-telly live from your own home, stick a 2.4 gig antenna up on the roof, and you could merrily be watching it live. You didn't have to wait for it to appear on the TV many months later. You were actually watching it live. But then I suppose as an employee of the government at the time, I sort of had a license to receive this type of stuff. So 2.4 gigs, it's been the pain of my life right the way through my entire career. 2.4 gigs is a very, very useful band, but I think there's a lot of people going around now that's saying it should just be killed off. It served its use. Let's just leave it to all the garbage devices, all the Internet of Things, and let's just leave 2.4 gig behind. But unfortunately, it's still around, and it's still got a very large number of legs left in it, and it's still working. So Then around sort of when I left the government service, I started doing some consultancy work and doing sort of IT technical training, more to do with PCs and networking and that sort of thing, and then started getting involved in becoming involved in the MikroTik stuff. As I say, never looked back since. Then in last year, as a sort of culmination of my training, I think, was when we hosted the first MikroTik Router S training boot camp at MikroTik Center in Riga. They've got a fantastic purpose constructed. Well, the building's not being designed on purpose for this task, but certainly the building has been modified very sensitively, very cleverly, very well indeed, as a training center. They've got a really cool sign on the roof as well. As you can see on the roof, it has the MikroTik logo, makes it very obvious to the local people who's in there. It's black in the daytime, and it goes white at night. You have to see it to believe it, so please do. We've got another training camp coming up in June, and we would love to meet you there. We're doing a special deal at the moment if you come to our stand, and we can do you some prices on coming to see us to do some training. We're spending the Wednesday in the city. Riga will blow your mind. Riga is an amazing city to visit. It's everything from beautiful in architecture, great people, really friendly, and it's a great place to go and visit. So we're doing the Wednesday as a guided tour around the city with training padded out on either side. So there's the theoretical, tough brain, difficult stuff on each of the side. There's like a sandwich with the meat in the middle being the great fun, having a day out with some professional guides, going around the city, and we explore the place and have some good fun. So have a word with some of the guys on our stand. Right, well, that's the end of the advert break. Let's get back to the purpose of my presence here today. So CAPsMAN makes it really easy to set up multiple APs. Probably not very much purpose just having one access point controlled by CAPsMAN. But once you get beyond about 2 or 3 or 4 APs, having them controlled by a central controller such as CAPsMAN, you suddenly find you get some immense benefits from doing so. Let's have a look at the Wi-Fi industry generally. You may have installed an access point at home. You may have customers who come to you and say, I've done this, it's really easy. Wi-Fi is really easy. I've got one single access point at home. Okay, it's down the back of the TV set, it's on the floor, doesn't quite make it up to the upstairs bedroom, but hey, you know, it even goes out into the back of the kitchen, it works great, so why can't I do the same thing in the office? And you're trying to then sell them the idea that no, you want a proper access point mounted on the ceiling, you need to have it installed correctly, you need more than one AP. But I've seen the adverts on the TV. The local big ISP in the United Kingdom, British Telecom, BT, they did a whole month's worth of advertising of their new router that they were supplying for home domestic retail use was so good that you could pick up the Wi-Fi from 300 feet in the air and hanging off the bottom of a helicopter. Because they were showing the guy with an iPad on the ground going, whoa, wow, I've got great Wi-Fi. And then he grabs hold of the legs of a helicopter and goes flying off up into the sky. And look, wow, I've still got great Wi-Fi. It just doesn't work like that in the real world, does it? Anyone who's ever used Wi-Fi has found that just throwing an access point in somewhere isn't really good enough. We often leave it just on automatic to work out what channel to use. 2.4 gigs is the main point of my conversation this morning. 2.4 gigs is the one that's going to give you the most grief, the most problems. So on 2.4 gigs, we've got 13 channels. If you're lucky to be living in Japan, you've got 14. If you're in the States, you've only got 11. So why not just put it on any one of those 11, 12, 13, 14 channels? Why not? Why can't we do that, guys? They're overlapping. When Wi-Fi was first coming out in the 90s, the radio channels were much narrower, were slower speed. They didn't need as much radio spectrum to send the information between A and B. So when the channelizing plan was designed, they did it with a 5 megahertz increment. So the channels were very, very, very short distance between the channel numbers. So these are just channel numbers. They're not really channels. In actual fact, on 2.4, because we've only got 3. You might possibly be able to get away with 4. There are some people who advocate a 4-channel plan, but it's probably, in my experience, safest to just use a 3-channel plan, which is 1, 6, 11. Now, if you leave it on automatic and you look at a MikroTik scan list, you'll have all the channels in there. And you've set it to auto. So the MikroTik boots up, scans, listens, and finds that perhaps the best channel is channel 1, 2412 megahertz. And it then sits there for days and days on end. That's fine in the home, but if you do it in a commercial installation and you put, say, 12 access points into a building, if they all switch on at the same time, they will all scan at the same time, and they will all find that channel 1 is quiet. So all of them will all come up and all operate on channel 1. We've now got a problem with interference. So we don't. We manually set them 1, 6, and 11. So we've got this problem that it's really easy if you just leave it at the default settings, and it's really easy if you leave it on automatic. And those who don't have enough skills to understand about Wi-Fi, you will have problems discussing it with them because they think it's really easy, and it's very, very straightforward, simple thing to do. Just throw some more access points in if it doesn't work. If there's not enough coverage, throw some more access points in. Leave it all on automatic. Leave it to the default settings. It'll be fine. It'll work itself out. Except it doesn't. It's amazing, actually, how bad Wi-Fi can be with respect to how you've installed it. I've gone to installations where they have thrown all the rules out the book. They didn't even know the rules existed. And they've put loads and loads of access points into hotels. They've put access points into buildings. And they've just put more and more access points in. Or we need more capacity. We need more throughput. We need higher speed. We need to have more clients. We need to be able to deliver a better service. Put more access points in. That will solve the problem. No, it doesn't. Here's a fantastic tweet from a vendor where it's saying that the guy is saying that he had fantastic Wi-Fi in the hotel. Absolutely pleased with it. Absolutely loves the product. And then took a photograph of one of the APs and how it was installed in the hotel. What is it immediately adjacent? It's an emergency light. It's one of these like 12-volt battery powered, maintained safety lights that if the electricity fails, these things come on to light up the corridors in the hotel so that you can still safely get out of the building in an electricity failure situation. And where have they mounted the AP? Right next to the metalwork of the steel box. And yet it was still, the customer was happy, which is why he tweeted how fantastic and wonderful it was. Well, that's actually one of the things about Wi-Fi. It is actually designed to degrade, and it degrades safely. It still hangs on with its fingernails and will provide a connection even in the worst possible situation. It's a brilliantly, amazingly designed protocol. So let's have a look at some of the other mistakes that people make. Don't put enough APs in. This is the scenario where my one single router in my house covers the whole house. Therefore, I only need one router, one AP for the entire office block. So that's a problem. We then have gaps in coverage, and it doesn't work in some areas. Too many access points. We haven't got enough coverage. We haven't got enough throughput. We don't have enough capacity. Let's throw some more access points in. Everything's set to automatic. Everything all on the same channels. We leave everything set to the default settings. They run at maximum transmitter power. An access point running at maximum transmitter power will be far, far louder than the mobile device trying to connect to it. The mobile tablet, your mobile phone, is the weak link in the chain. The mobile phone has a much weaker transmitter power than the access point. So therefore, there is no point transmitting very, very high power from an AP if it can't hear the reply coming back from the mobile device anyway. What actually happens is by running it at full power, by running it at maximum transmitter settings, you end up actually shooting yourself in the foot, because you're now making the access point transmit much further than the client devices can even connect to it from. So they are hearing the AP, they are picking up the signal from your AP, and they are trying to connect to it, because it's coming in loud and clear and coming in really well, not getting any reply. Well, that's because the AP can't hear the device that's transmitting to it, because it's too weak. And it's also probably being interfered with by other access points on the same channel that are also too loud. I can safely say that major ISPs do not understand Wi-Fi at all. They will ship routers like Technicolors, TP-Links, Draytex, all the major vendors. They will have them pre-configured with their standard configuration on them. There are companies that will provide this service for you, and they just need to be told your customer's address, and they will ship your customer a router already set up with your favorite SSID, with your favorite username and password, and your favorite basic default settings. And one of the things that they think is a clever idea is to set the 2.4 gig AP to 40 megahertz. Plenty of bandwidth, lovely high speed, it'll work fantastic. Be cool, won't it? Be great. We got the best router than any other ISP in the business, because we're shipping all of our routers with 40 megs on 2.4 gigs. Nobody else is doing that. They must be stupid. No, I'm sorry, you're stupid. Because clients, the vast majority of mobile devices do not support 40 megahertz on 2.4 gigs. They will talk to the AP at 20 megahertz. So the AP is advertising, I can do 40 megs. And yet the client device will say, well, I can only do 20. Okay, then I'll talk to you with 20 megs then. What a waste. So the AP is advertising something that the mobile devices don't even support. Pointless. So therefore, if you're deploying this stuff, don't configure 40 megahertz on 2.4 gigs. But then what about 5 gigs? Now, MikroTik at the moment are not doing a Wave 2 AC model at the moment with 160 meg channels, but they are certainly doing 80 megs. Now we have a problem with lack of spectrum. If you put out a lot of access points into an office, enterprise, warehouse, building, large deployment site like a hotel, etc., you're going to very quickly run out of channels. Plus, on top of that, the way in which the Wi-Fi protocol works is as you double the bandwidth, so as you go from 20 to 40 to 80, it halves the transmitter power. So by the time you go from a 20 to a 40 to an 80 channel width, you end up with quarter of the power you started off with. So everything is now working with weaker signals, more noise as well. If you are going from 20 to 40 to 80, you are listening with a wider amount of radio spectrum. You are listening to much more channels. You are now increasing the potential of receiving interference from other APs and other mobile devices on the radio spectrum. So you will not see, unless the location is incredibly quiet and has got no other interference and no other access points that it can hear, it is highly unlikely you'll get any real benefit. In the home, at your own home, with just one AP only, on 5 gigahertz, you can get away with 80 megs. Because you usually have got enough distance and enough isolation from your next door neighbor. If you're living in a built-up area, if you're living in an apartment block, and you're in blocks of flats or you're high up off the ground, then probably not. Because there's going to be other people using 5 gigs, and they will severely reduce the throughput and the speed of your Wi-Fi running 80 megs. So don't use 80 megs. Use 40. If it's a very high density deployment, like you're doing a major conference, an exhibition, theatre, sports arena, you'd only use 20 megahertz. You don't use even 40. So again, it's very easy to be lazy and to think, what the hell, let's go for maximum speed, maximum performance, let's knock it up to 80 megs. Don't do it. You actually are going to, again, make a mistake for yourself and shoot yourself in the foot. One of the other mistakes I find is that people run speeding tests to speedtest.net. And they'll go from room to room with their laptop, and they'll do a test to the internet. What are you actually testing? Are you testing the performance of your Wi-Fi installation? No. You are testing the performance of your Wi-Fi installation, your local LAN, your switches, your cabinets, your cabling. You're also testing the speed of your edge router. You're testing the speed of your internet provider. You're testing the speed of the internet. And you're testing the speed of the servers at those people who are kind enough to offer the speedtest.net hosting. You're not testing the Wi-Fi. So stop using speedtest.net to prove to yourself whether it's working well or not. The other risk is that you can't guarantee that you're connected to the access point that you're sat underneath. The way in which mobile devices work is if they are happy with the connection that they have at that moment in time, you can walk with that laptop and be sat right underneath a brand new AP that you've now moved yourself underneath, but you're actually still connected to the AP next door. Because Wi-Fi protocol says, if I've got a strong enough signal, if I've got a good enough connection, I'll carry on staying connected to next door. So you could walk into the next room and do your speed test. You're not testing that access point. You're testing the one you're still connected to. The other mistake I find that people make is looking for the magic golden 4 to 5 bars coverage. I've walked around the house, I've walked around the office, and my phone is getting 5 bars of Wi-Fi. It must be fantastic. It's got to be cool. It's great. It's wonderful. I can walk off site happy that everything's working really well. And what is that really telling you? It's really telling you that all of your access points are shouting nice and loudly. Now, you know what it's like if you're in a room with a lot of people shouting. You can hear me because I'm the only one who's shouting. Or at least the speakers are allowing me to. So I'm the only one, so I can be clearly heard by you. But if all of you were all having these conversations and all of you had a microphone and all of you were all talking at the same time with the same volume, I don't think we'd have as easy a task as we've got at the moment. So communications would break down. But just simply walking around with a phone and going 5 bars, 5 bars, 5 bars, fantastic, that's not proving anything. So don't do that. So when you are dealing with the home environment, it's traditionally not as intense. It is not traditionally as important in the sense that the amount of connections that are being made is low, the number of devices is low, probably half a dozen, maybe a dozen devices connected in the house, not a huge number of devices, and it's unlikely, normally, that all of those devices are all demanding high levels of throughput all at exactly the same time. So you may have 2 or 3 devices in your possession, but you won't probably be using all 3 of them all at exactly the same time. You'll pick up your phone, send a tweet, put your phone down and go back to watching the TV that's streaming Netflix over Wi-Fi. You might then pause the Netflix and go into the kitchen and make yourself some dinner. So what's happening with the Wi-Fi in the home is it's much more on and off, on, off, bursty. Maybe some demand and then nothing, bursty, then no demand, then nothing, goes quiet again. So it's much more relaxed and it's much more slower in its demands. And you probably don't really realize actually how bad the Wi-Fi is in your home. You might be mobile, you might be walking around the house and not realize that your phone is constantly connecting and disconnecting. You don't care. There's so much buffering going on that you can take an iPad watching YouTube and you can leave, as you know, You can leave the Wi-Fi completely for a few seconds, reconnect. You have no visual clue, no visual indication that the laptop has just disconnected from YouTube for 5 or 6 seconds. Because of the buffering that's going on in the background, it just carries on. So you can get away with it in the home, and you don't notice that the problems that are actually probably there all along, you don't notice them, you don't worry about them. It's when you come to a high-density Wi-Fi installation, which is where this physics, the laws of how Wi-Fi works, starts to become much more important. We're now going to start putting it under strain. We're now going to push it to the limits. We've got quite a few hundreds of people in here. And not all of you are listening intently to every word I'm saying. Somebody's going to be tweeting, somebody's on Facebook. You're all using the internet all the time. And the APs that have been installed in here by MikroTik are doing a reasonably good job at keeping up with it all. But it is under heavy load, and it's being pushed. And I bet all of you have all experienced at some time yesterday and today, lack of connection. You all must have done, and that's because we're really putting it under intense pressure now, really pushing it to the limits. And that's when people notice it. So when you go from someone who's a plumber, an electrician, he's a carpenter, he's a builder, and he has installed the Wi-Fi because he's seen other people do it and it's really easy, he can get away with it. It's then when he then gets the contract to install Wi-Fi into a sports stadium because his best mate is the manager of the football team, and he said, I do Wi-Fi all the time. I'm a builder by trade. I usually lay bricks and dig foundations in the ground. This Wi-Fi stuff is a piece of cake. It's really easy. You just chuck it in, it works. I'll do your football club. I'll stick it in the stadium. I'll give everybody Wi-Fi. Probably 2 APs will do it, I should think, for the whole football ground. It'll be a piece of cake. It'll be easy. I'll even put some access points in the offices for you as well. And then they phone us. It doesn't work. Well, there's a surprise. So the other thing about Wi-Fi is when people come from the networking and the cabling world, trying to find a fault is really easy. You can see it with your own eyes. Here's a rat that has chewed through a Cat5 cable. You'll spot that really quickly. And that would explain to you very quickly as to why that circuit is not working anymore, because some animal has chewed through it. Wi-Fi doesn't work like that, unfortunately. It's invisible. So when there's a problem with Wi-Fi, when there's a problem that is invisible, how do you actually see it to fix it? Well, we're going to need to have some tools. We need things like spectrum analyzers. We need diagnostic tools that really will dig down into the more deeper parts of how the Wi-Fi works, rather than just doing a ping test or a speed test. So what about some of the problems that you're likely to see on 2.4 gigs? You name it, it's been there. Microwave ovens are on 2.4 gigs. That's how it cooks your chicken dinner, because it puts lots of 2.4 gigs RF at about a kilowatt. So we're dealing with 1 kilowatt of RF from a magnetron going into the metal chamber. You'd be surprised how much 2.4 gigs leaks from your microwave. I can bet you most of you have gone up to the glass of a microwave oven and put your nose against the glass to look inside to see if your dinner is ready yet. Please don't. All right? Because there's a lot of RF coming out of a microwave oven, much more than you could imagine. Which means that if you try to deploy an access point on 2.4 into an area which has a microwave oven in it, when they're cooking, it won't work. CCTV, very, very low cost. You can get them, tiny little module with a single lens. It's a small cube, and they put a 9-volt battery on it, and then that gives you a small little camera, 2.4 gigs. Bluetooth, of course, runs on 2.4 gigs. Video senders to get the video and audio from your TV from one part of the house to another, they're on 2.4. I've seen a lot of burglar alarm motion sensors. You know, the things that detect movement in the corner of the rooms with a little red LED on them that flashes as you move around. There's a large number of those that are manufactured with a 2.4 gigahertz transmitter built into them. That is going to interfere with your Wi-Fi, and you won't see that when you're walking around with your laptop, because these motion sensors do not advertise an SSID. They don't advertise themselves because they're not Wi-Fi. So they won't be visible on your laptop. You'll need a spectrum analyzer to find that. USB 3.0 runs at 1.2 gigabits. What's 1.2 multiplied by 2? 2.4. And unfortunately, if you've got any USB 3 devices anywhere near where you're trying to receive 2.4 gigs, it could easily wipe it out. They are quite noisy, certainly if you don't get high quality cabling, high quality shielded with the RF chokes, the lumps of iron glued around the cable to limit the RF radiation from them, they will wipe out your 2.4 gigs. Zigbee, home automation, all running on 2.4 gigs as well. Lots of stuff. The one things that are really disruptive are those that stay on the air all the time. Wi-Fi goes on and off all the time. It transmits, receives, it's half duplex. It does not transmit all of the time, which means there's always an opportunity for someone else to get in and to transmit in the free air time. Things like burglar alarms do not work that way. They are permanently transmitting with 100% occupancy. I've got a slide later on which shows an example. So what's the other big thing that really causes the major amount of interference on Wi-Fi? Is Wi-Fi. Other Wi-Fi devices cause interference to other Wi-Fi devices. It's designed to do that. This is how they can all share the radio spectrum. They're able to share this medium, what the Victorians used to call the ether. So they're able to share it. And that means that you're always going to be receiving other 802.11 Wi-Fi signals as well. So you're waiting for them to shut up, you're waiting for them to stop transmitting before you can get your foot in the door, and you are then able to transmit your packet. That's the way it's designed to be. It's called co-channel interference, or it's sometimes abbreviated to CCI. That's normal, that's what it's designed to do. So the mechanism that's actually used to do this is called carrier sensing, multiple access, CAPsMAN more specifically. We teach this on things the MTCNA and also on the MTCWE. So if you've got those tickets, you should really know that one by now, because that's fairly low-level stuff. But built into that mechanism of gaining access to the channel, there are actually two methods. There is a method which is called clear channel assessment. And this is a mechanism built into the hardware and reporting to the software layers of the chipset. It is a system whereby the radio is trying to work out, is there anybody else using the channel? Can I talk, yes or no? To allow the software to make a decision to transmit or not. And there are two basic things that it's looking for. It's looking for energy. It's called energy detection, ED. And that is for all the interference that is not 802.11. And then the other mechanism is proper, genuine decoding of 802.11 headers. So when an 802.11 Wi-Fi transmission comes on the air and begins to transmit, there is a physical header which is placed at the beginning of every transmission. And if anybody on Wi-Fi that's listening to that channel is in a position to be able to get a strong enough signal, they will successfully decode it. Now, one of the things that's embedded within that header is, for example, how long the transmission is going to take. So in that first part of that header, you've now informed all the other 802.11 devices on that radio channel within reception range. You've just told everybody how long you want the channel for. So if you've told it you want it for X amount of microseconds, everybody else now knows to back off for that amount of time. If, on the other hand, we end up with a non-decodable transmission, something like a burglar alarm sensor with 100% occupancy, and it's a strong enough signal to be detected, which is usually set at a level which is 20 dB stronger than the 802.11 detectable level, so it's down to the chipset as to what that level is set at. So that's quite a strong signal. It's 20 dBs more than a normal Wi-Fi signal is decodable at. It will wait. Because the decision engine, the actual decider, says there's energy there. It's strong energy. I'll wait for it. 3 days later, it's still waiting for it. Because the rules of 802.11 is that we have a shared medium. And only when everyone else has shut up do I get an opportunity for me to do my thing and to transmit into the channel. And so if you've got energy there, which is non-802.11, it will just beautifully kill the operation of that radio channel. So here's an example of a spectrum analyzer. We have got a steady amount of energy. You can see it's 100% occupancy because in the waterfall plot, we've got a solid red line. It's a solid vertical red line, which means this transmission has 100% occupancy. It never, ever, ever stops transmitting. Which means if you're trying to do Wi-Fi in this building, where I got this from, it's not going to work on those radio channels that overlap that frequency. Because the chipset will just back off and say, I can still pick up energy. There is someone out there still using the channel. I mustn't. I have to wait. So you need a spectrum analyzer to see that, because it's non-802.11. So the actual carrier sense part, which actually looks for the 802.11 header, will genuinely pick up the information required and work out how much transmission time to back off for. That's fine. That's cool. That's great. Because that means you are making sure that every device is informing every other device within range of how much usage is going on. So they now get a better chance of getting in there because they can go to sleep. They can go into power save mode. Because while someone else is transmitting, they don't need to do any receiving. So they can shut down the chipset and actually switch off the receiver for that amount of time and only wake up and start listening again when that time has concluded. So regardless of which it is that's making the decider, is it energy or is it a proper genuine carrier sense, so actually decoding of the header, the busier the channel, the more active the channel, the more things on it, the slower your throughput will be. So what are some of the things that we can control in CAPsMAN? What are some of the things that we can actually do to help reduce the wasted time taken by client devices and AP devices to speed the process up to give more airtime for real, genuine user data? Well, there are three major types of contention or co-channel interference from 802.11 devices. You've got all the clients all trying to fight for airtime to try and connect to the AP. So that is all the clients listening to the AP and listening to the clients immediately around it and waiting for a moment when it's gone quiet. You've also got the access points themselves. They're also listening. Access points are not God. Access points do not have the power or the right or the permissions to talk over the top of a client. There's nothing special about an AP. It doesn't break the rules of 802.11. So if you've got a lot of access points and they can all hear each other because they're all on the same channel, then all of the APs will all back off and will all wait until the other one has stopped talking. Which is another reason why we don't have all the APs on one channel, and also why we don't put all of the APs within sight of each other, so we distance them from each other. Get some isolation between them if they are on the same channel. The other problem is that we have is, what about clients that are connecting to another access point that is actually on the same channel? Imagine a situation where you've got two APs, and because of your channel plan and because of the design of the building, you have made sure that those two APs cannot hear each other. Imagine this situation here in this room. We've got metal walls, metal doors. I could possibly get away with putting an access point on the same channel in here as in next door. But what about a client belonging to a person standing in the door? They may be communicating with the AP next door that's on the same channel. I can hear them. So I, in this room, on this AP in here, has to wait for that client in that doorway to stop communicating with the other access point before it gets the time to transmit to the other devices in here. So if you are going to do that and you're going to start separating the building up and putting isolation in, using the building to your advantage, to be able to reuse the channels as much as possible, look at the design of the building and the design of your plan of what's in the middle. What's in the middle? Are there likely to be a lot of devices hanging around in that area that could actually be causing you a leakage, effectively, and leaking the lack of airtime between the two zones or the two cells? So here we've got a problem that everybody's fighting for the time. All of the clients are all listening, and so is the AP, and the AP is listening, all waiting their turn. We've got access point to access point. They're listening to each other. So these two APs can hear each other, and both of them will back off and wait for the other one to shut up before they take their turn, which means we're down to 50% of the available airtime. Because if they're both sharing it, there's two of them, they both get about half each. We've just lost half of our throughput. The other issue is if we use repeater mode. If you use the MikroTik feature, where you can put an AP and a station onto one physical device in repeater mode, what you've effectively created is a very, very large cell. You've joined those two APs together as if they were one. You've extended the range, and repeaters are fantastic tools. I was certainly one of the ones asking MikroTik for a long time to do this, and it really does serve a very, very useful purpose to get you out of jail, especially if you go to a hotel and they've got rubbish Wi-Fi. That repeater mode can get you out of trouble. It's a great, great, great feature. It's fantastic. With a map light, you can have an AP and a station all in one device. It's cool. But remember, you are extending and repeating, and therefore that means you are waiting for half the airtime. That's how 802.11 works. So this is the example now of the client that's sat in between the two. You've separated the access points. You may have put some physical property in between, like the steel structure of the building's in the way, and you therefore now think that the two APs are separated from each other. No, they're not, because you've got clients sat in the middle that will wait for each other to stop transmitting because they can still hear each other on the same channel. And nobody, remember, has any more rights than anyone else. APs and clients have equal access rights. So AP to AP contention is actually very, very common. And that's because we tend to mount the access point up high. We'll put it up on the ceiling, we put it high up on the wall, which means that they get very, very good visibility. So here's an example of an exhibition. We've got a couple of CAP ACs. They can see each other. Down on the ground, when you're walking around with a laptop, you might think there's enough separation. But the APs can hear each other because they're up nice and high in the clear and in the open, and there's nothing in the way. And so they're both of them going to be coming through loud and clear to each other. So we really do need to make sure that we keep same channel APs as far away as possible from each other. This is very, very difficult on 2.4 gigs because we've only got 3 channels. This is why I hate 2.4 gigs. So we try and use the building, try and use directional antennas. A lot of the AP products have got omnidirectional antennas in them. Omnidirectional antennas therefore mean it's cheap, simple, easy, convenient, but dangerous. Because it now means that you're flooding the Wi-Fi in a full 360-degree direction, which may not be appropriate. It might be you only need 180 degrees. It might be you only want 90 degrees. You might be running into a warehouse, putting access points into a warehouse. You've got all the shelving. But the people on the ground with their barcode scanners logging the goods in and out, they're not going to be climbing into the racking, so you don't need Wi-Fi in there. You only need Wi-Fi in the lanes. So therefore, put Wi-Fi in the lanes. Don't use an omnidirectional. Use a directional firing up the lane and only doing Wi-Fi, firing up like a beam going up the walkway between the racking. So 802.11 is designed to cope with this. And that's why, although it's called properly, it is called co-channel interference, I don't see it as interference. This is how Wi-Fi is designed. It's contention or congestion, really, more than actual interference. If you have overlapping radio channels, like someone deploys access points on channels 1, 2, and 3, then the other APs on the other channels will not be able to decode the header. And because they can't decode the header because they're overlapping, it's seen as interference and noise. And because it can't decode the header, it can't work out how long to wait for, which then means it just keeps on listening and uses up more battery power. And the device is going to keep on listening. Oh, the noise has gone. Now can I transmit? So it becomes much less efficient if you're using overlapping channels, because the overlapping channels will mean that the devices are not able to cleanly and perfectly decode each other. I would prefer to have co-channel interference than, say, adjacent channel interference, where the channels are overlapping and it's just coming up as noise and interference. I'd much rather that the devices decoded the header and worked out the precise amount of time to back off for, than for it to not to know and for it to just pick a random number and wait for random time. I've done that, I've said that. So access points are sending out beacons. This is how we know how to find them. We go on our phone, and our phone gives us a list of the access points so that we can connect to. But those beacons that are transmitted don't just transmit the name only. It transmits a lot of other stuff as well. There are whole loads of extensions to the original 802.11 protocol. There are all these others like 802.11e, 802.11d, 802.11r. There's bucket loads of them. And they're all transmitted in the beacon and advertised by the access point. So the access point is saying, I'm not just a standard Wi-Fi product, I can do all this extra stuff as well. And that all adds time to the transmission. Because as you enable all these extra features in an access point, it adds more transmission time because it has to transmit all these extra frames, you know, all this data has to be built up into a beacon, and it takes up air time. The other thing about a beacon is that it's unique to the SSID. So if you have configured your access point with 4 SSIDs, maybe for corporate, guest, the warehouse, for some testing. So you've got 4 different SSIDs. That's going to take up 4 times as much time. 4 times as long now before anyone else gets a chance to transmit. And those beacons will be transmitted and consuming time. Time which your clients much probably would rather have for sending usable data rather than listening to more beacons. The other thing about beacons is that beacons are used to identify an access point for you to connect to, which means that the access point is expecting it to be received by clients it does not know about. So it does not know what the capabilities of the client are. It can't talk to the client until the client talks to the AP first. So it's not until the client knocks on the door and sends a probe and actually advertises what its capabilities are like. That's the first time that the AP knows what the client is capable of. So therefore, to make it fully compatible with all the clients in the world, the beacons are transmitted at the slowest rate of all. Because then that caters for everything. And it means that it's guaranteed to be receivable by all of the mobile devices out there. Now, if you're running 802.11b, those beacons are going out at 1 megabit bits per second, and it's really slow, and I'd wish he would hurry up. Okay? So if you're using 802.11b, transmitting those beacons at 1 megabit per second, that's a hell of a lot of time wasted when you know the client supports G or supports N. So why the hell are we forcing the beacons to go out with B rates? Because that's the standard to make it fully compatible with everything that's ever been there since the year dot, since the 90s. So we've got a problem. So putting more SSIDs on wastes time, and it takes time away from client data. We can actually remove the slower data rates on the beacons. There's nothing to stop us from doing that. It's in the standard. That's one of the cool things about the way in which the 802.11 standard was created, is it's very flexible as to what it allows you to get away with and still work. So what we can do is we can get rid of that B. We'll just stop advertising it completely. We'll just ignore any clients that might come onto the network that are B only. And we just say, forget B, and we just do G and N. And then once we've got G and N being advertised, we can then go one step further and take away the slower data rates that G and N will advertise, which is 6 megabits per second by default. So the client will always make an initial probe request using the slowest speed of all, because it also does not know exactly what the access point will be happy to connect with. So it will probe the access point to say, I'd like to connect to you, and it will do that at 6 megabits per second. But at that point, it will then transmit back to the client at whatever you have configured on CAPsMAN as being the slowest basic data rate. And now the client says, oh, so you're not talking to me at 6, you're talking to me with 12. Okay, from now onwards, I will communicate with you at 12, or better, depending on the quality of the signal. So do bear in mind that even if you set CAPsMAN to ignore 6 megabits, it will still receive the 6 megabit probe. There are times in life where when you write a support ticket to MikroTik, you regret doing it when you get the reply coming back. Because I configured a wireless link and I removed 6 megabits. And yet I found that when I was doing Wireshark and I was looking at the packets, I was actually finding a very large quantity of 6 megabit packets still being transmitted. And I had done the AP and the stations and removed 6 megabits. And I sent a support ticket in saying, why are you still using 6 megabits when I have disabled it? And the reply came back saying basically, yes, of course it does. What do you mean, yes, of course it does? And then I started thinking about how 802.11 works, and their answer was completely correct. It has to always still support 6 megabits for the first transmission, but from then onwards, from that point onwards, we can raise it up. So you'll always get 1. So, I don't have time. Oh, we're cool. So, 2.4 gigs versus 5. I would rather ditch 2.4 gigs completely. The majority of mobile devices now are capable of supporting both bands. And the cool thing about using 5 gigahertz is there's a heck of a lot less interference and there's more channels. Therefore, it's a good idea to try to encourage the mobile devices to go to 5 gigs. Has anyone analysed the mum Wi-Fi here? Anyone got out of their way to have a look at it? How many 2.4 gig APs are running here compared to 5 gigs? There is something like about 3 or 4 APs running with 2.4. All the rest are on 5. And why is MikroTik doing that? Because that's best practice. Make the majority of the clients, force them to use 5 gigs by giving them a much better signal on 5 than on 2.4. Make the 2.4 rubbish, make the 2.4 gigs weak, make the 2.4 gigs rare and sparse, so it's very rare to find a 2.4 gig AP with mum on it, and that will then force the client to scan 5 gigs and find a better one. Because 5 gigs is a hell of a lot better than 2.4. So that's the theory. Why is it so important? because this is how we're going to make things get better. So let's now get into the nuts and bolts of what we need to do. So let's just basically design it so we have as few SSIDs as possible. There are methods by where you can allocate VLANs to each SSID connection. You can say one single SSID for everybody. But with Radius and with the way in which you can configure CAPsMAN, you can set it up so that the clients can be grouped together, that even though they're all connecting to one SSID, when they authenticate, they are allocated a VLAN tag so that the traffic coming between the AP and your switch will be tagged with a VLAN tag with one SSID. And yet you could have 200 client groups, all with 200 odd VLANs, and yet one SSID. There are ways in which you can do this. So try not to go above about 4 or 6 absolutely maximum. The lower the better. Remember what I said about the beacons will transmit extra information if you enable it. That wonderfully, very, very low, secure WPS mechanism, which is now available on MikroTik wireless devices, turn it off. I mean, there are security vulnerabilities with WPS anyway, but if you turn it off and disable it, what happens is that it reduces the size of the beacon, because it's no longer going to advertise that it's capable of doing WPS, and now we've got more airtime. Avoid using 802.11b. Turn the power down on 2.4 gigs, so you go into the CAPsMAN interface and physically drop the power down. You need to typically bring it down by about 7 or 8 dB compared to a 5 gig on the same radio. So if you've got a dual band access point, dual band with 2.4 and 5 gigs within it, you can leave the 5 gigahertz running at full power, but you drop the 2.4 by about 7 or 8 dB. And then that actually will start to make the client think otherwise and start to make the client make decisions to go to the 5 rather than the 2.4. You also know, I'm sure, that 2.4 goes further into a building than 5. It is receivable by clients further away from an access point than on 5. So that is also another reason why we drop the transmit power on 2.4, because it goes further. The other thing we can do is use human psychology. If you label an SSID and call it slow internet, and on their phone they also see another one which says fast internet, which one are they going to connect to? Fast. I'll have the fast. So you're using the power of the mind to convince the customer to do your work for you. There's your band steering. Who needs a clever button on the access point to do it for you? Use the SSID names. So on 2.4 gigs, make a suggestion to the human psychology that it's a rubbish connection to go on, and then they'll all go on to the 5 gigs. If you are going to use 2.4, we use channels 1, 6, and 11 only. Also, if you're using 5 gigahertz, what is the problem now? I did a talk about this at the London MUM, DFS. I'm just hoping that the fire alarms don't go off. 5 gigahertz has the downside that it's sharing spectrum with other users, and they are radar. And that means that the access points have to comply with some additional technical standards to listen for this radar, and if it thinks it has received some, it shuts the access point down on those channels. What's going to happen to all your clients that are connected to that AP at exactly that moment? Gone. What the client's now going to do is they're going to start scanning around and try and find another AP to connect to. So the risk is there may not be another one nearby. So if we had only one AP in here on 5 gigs and it suffered a DFS event and it dropped the transmissions, let's maybe say for half an hour, where are you going to send the clients to? So if you're going to use DFS channels, do. It's fine. Inside a building, you can use DFS channels quite reliably, but you have to take into account the possibility that it will go offline. And if it does, plan for it by allowing the clients in that location to connect to something else nearby, which is still going to be up and running because they will not have suffered a DFS event. So what 5 gig channels do not have to do radar detection is the bottom 4 channels. Channels 36, 40, 44, and 48. They will never go offline unless the AP fails. But they will not go offline because of radar. Because those 4 frequencies do not have to look for radar. They do not have to comply with the DFS regulations. So that then gives you the capability of providing another 5 gig signal nearby that won't go offline. But if you do your plan using only 4 channels because you want bomb-proof reliability, you've only got 4 channels available to do it with if you're using 20 megahertz. And we're getting back into the world of what 2.4 gigs is like if you do that. You have got to use DFS channels, really. They're using them here, and it works. The other thing, as I said, was that CCI, co-channel interference, occurs between the access points, between the individual APs. So what we can do is we can now, with CAPsMAN, we can now do background scanning directly from the CAPsMAN interface. So you don't have to log into the CAP, because what we used to have to do was you log into the router board, which is running the CAP. You have to disable CAP mode, go back to being a normal standard radio, and then do the scanning. And then when you're finished, re-enable CAPS mode, and then go on to the next AP. Don't have to do that anymore now. We've got background scanning directly from within CAPsMAN. So what we can do is we can just right-click the interface, the CAP interface, we can just right-click, do a scan, and we won't drop any clients. The clients will remain connected, will remain using the CAP, they're none the wiser, and you'll get a nice background scan. What you can now do is filter the view. If you do it if you sort the fields, the columns, on frequency order, you can look for the same frequency that that AP is running on, for example, and find out the signal levels of all the other APs on the same frequency. So here's an example where an AP is able to receive 3 other access points, and they're all around neg 85, neg 87. That's fine. That's weak enough. It's not going to cause airtime issues. So the AP will not wait for those other APs to shut up before it grabs the channel. So we can then move on to the next access point and check to see if that one's can pick up, and yes you do. You work your way around, and if you've changed any of the radio channels on any of the APs, you have to start again. And you keep going round and round in circles until eventually you've done the lot. Anything above about neg 70 is fine. And when I say above, I mean less than. You know, a number greater than neg 70 is usually around fine. So what about how we actually configure CAPsMAN to take out some of these basic rates? You can take out 6 and 9 and just leave 12. Some clients, and I say some clients, don't like the removal of 12 megahertz. Megabits. They don't like the removal of 12 megabits. So be careful about going crazy and setting it to 24 or anything even higher than that. But certainly, I don't think I've ever found any client anywhere that suffers any negative impact on having 6 and 9 removed from it. But test with the customer's own device. Your laptop is not going to get left behind. You're going to take that home with you. So don't do any surveying work using your own laptop. Grab one of the customer's devices, possibly from a customer that complains a lot, and take their device around the location to prove that it works. So in CAPsMAN, we have this hierarchical configuration. We have the interface which overrules everything else. Whatever you configure on the interface will override any other settings beneath it. One of those is the configuration settings. And anything you set in the configuration settings will override anything that you've put in the rates, the security, the data path, or in the channels settings. So it works basically, it works from right to left. So what's on the left has higher priority and will take over and set and replace anything that goes underneath it to the right. So for example, if we create a radio channel with a name of channel 1, and we call that channel 1, and give it a frequency of 2412, because that is channel 1 on 2.4 gigs, we save that, we can now assign that channel name that we've just created into a configuration setting. But on the configuration setting, we can overrule it. So yeah, I know it should have channel 1. I'm actually going to put in a frequency of 2437 instead, which is channel 6. And then you go to the interface, and you can overrule it again and set it to 2462, channel 11. So the end result you end up with on the status tab, looking on status is the end result. The status tab on the interface tells you what the result of all the lower processes all added up together will do. So let's get rid of the 802.11b. By default on the status tab in CAPsMAN, you will see that you're running B because it will show you that it's running 1 to 11 megabits per second. You can see it says CCK 1 to 11, and that means we are using 802.11b. Now I'm not suggesting you don't believe MikroTik, but I used a third-party tool to find out if that was true. So using a product called Wi-Fi Explorer Pro, which is available only for the Mac, I noticed that it is advertising B, G, and N, and it is advertising that the basic rates is 1, 2, 5.5, and 11. So that's it, that's your 1 to 11. So it is indeed transmitting beacons at 1 megabit per second and advertising that it fully supports 802.11b connections. So let's turn that off. So in CAPsMAN, we can define it on the channel. Remember this hierarchical layered system? So on the actual channel definition, we can set it to just do G and N only. We could do it on the configuration. We can do it on the interface. Oh, sorry, that's setting a channel, isn't it? Sorry, channel. But the end result will be we've got rid of CCK 1 to 11. You can see now it is showing that B has gone, but has it? So let's check our third-party tool. Look at that, B's gone. It's now saying we can only do G and N only, and it can only do 6 megabits per second. One of the things I wanted to look at, I haven't checked. No. Right. So we've got rid of it. But that's not enough. So we've got rid of 802.11b, we've got rid of it for where it belongs, in the bin. We now need to drop the rates. So the next thing we do is there is not a default rates. MikroTik does not provide you with a rates configuration with the default settings on it. You have to create one before you can edit it. So what I'm going to do is I'm showing you here what you have to create to just get your basic 2.4 gig settings configured. So there's your basic rate running at 6. It's also capable of supporting 6 upwards. So it will do 6, 9, and all the way up to 54 megabits per second. So that is all your G rates all there. No B rates. We've got rid of B. The 1 to 11 we do not need to advertise. So we've turned off the B by setting the channel to be GN only, and we're making sure that we do not use a rates configuration with any of the B rates in it, just only G. So the end result, if you apply this configuration to an interface, is nothing has changed. We're still advertising that it does 6 as a basic rate, and it will support between 6 and 54. So that's good. Now we play with it. So we get rid of the 6, the 9, possibly the 12, but I would try it with 12 as the lowest first. So what we do is we untick the 6, we untick the 6 and the 9 on the supported, and we then make sure that 12 is being advertised as our basic rate that it needs to connect with. End result, we've got rid of the 6. So now we've got a beacon that is telling the clients, I can only do 12 megabits per second. So you'll get your initial probe, the initial first packet coming from the client will be at 6. Can't stop that from happening because that's the standard. But the AP will reply to the client at 12. And from then onwards, it will never go below 12. Let's have a look to see if it really is doing that. So there we go. It's G and N only, and it's saying that the basic rate is 12. Okay, simple, isn't it? When you know. So for those who want some suggestions of solutions and software products, I really find there's a particular software developer that's been creating some fantastic software for the Mac. I'm a Mac lover for a very good reason, because I don't have to keep fixing it all the time, it just works. Or I get Normans to fix it when the display doesn't work. Wi-Fi Signal is a cool status tab program that just runs in the background, and it tells you which AP you're connected to, signal to noise ratios. It will alert you when you're roaming, and it tells you the devices that you're roaming to. It logs everything into a log file, so as you walk around a building, you can then look back at the log file and find out if you were roaming successfully or not. Wi-Fi Explorer is really, really good. That's what I've been giving you the screenshots from. And if you get the Wi-Fi Explorer Pro, I mean, look at it. It's 81 euros. It's peanuts. And for the amount of power that that tool provides you, it is a really good diagnostic surveying tool to find out what's going on. And you can add an analog spectrum analyzer to it as well. If you've got boring old Windows, then there's the Ekahau Heat Mapper, which is fine for the home and for small company and IT usage. That's completely free of charge. If you buy the full-blown package of Ekahau, you're looking at thousands, $4,000 or $5,000 for the full-blown package. There's also NetSpot available for both Windows and the Mac. There is a freebie version, but you can't do any reporting. It won't generate any PDFs. So you can't give anything to a client for the freebie version. And just the last thing, optimizing CAPsMAN. Try to use local forwarding, because if you don't use local forwarding, you're now hoping that the CAP is powerful enough and that the CAPsMAN is powerful enough. So if you are just running everything on like say a 2011, if you've got a 2011 as your CAPsMAN, which also you're controlling the Wi-Fi, the 2.4 gig AP that's built into the 2011, and also it's controlling another 50, 60 or so other APs in the building, I have found that if you use the manager forwarding mode, where it tunnels the traffic back to the CAPsMAN, you will not get as high a Wi-Fi performance as if you just allow it to be just dumped onto the local network with the mode which is called local forwarding, and that ends up with a higher throughput. The new fast path, I've been assured, is coming, but is not yet available, so we can't utilize the wonderful power of FastPath on the CAP at the moment. So the end result is we should end up with a better performance, more clients on 5 than on 2.4, higher data rates. We should have designed it that we got much less interference on it. Hopefully you've walked around with a spectrum analyzer and got rid of all the garbage that's transmitting 100% occupancy devices on 2.4. And hopefully the phone stops ringing with angry customers complaining about how rubbish your Wi-Fi is. Well, we can live in hope, can't we? We can dream. Right then, well, it's Easter. Well, it was Easter last weekend. Let's have a couple of Easter eggs. One of the things about MikroTik is they have this thing called a change log. Anyone bothered reading it? Yeah, some of you. Okay, I got myself to blame here. I would say to Normans and Aldis and the guys on the desk, will you please make the change log more verbose? Can you please put more information in the change log? Because you're just saying stuff like, we fixed stuff. Can you please stop doing that and just say you fixed things? What exactly did you fix? Tell us. Give us more information. Well, they've had the last laugh now, haven't they? Hey? And I'm not complaining. The change log now has one heck of a lot of stuff in it. So read it. And if you read the change log, you find things that get added to CAPsMAN which have not yet been fully documented in the wiki. So one of the things, for example, is the access list gives us the ability to control access to the access point. That's what the access list does. And a new feature that got added quite some time ago now is the interface lists. This ability to group a set of interfaces together under a common list name. So we had this ability to have like the WAN ports, or to have the ports that you wish to run neighbor discovery on. So we've got the discovery dynamic interface lists that get created. So all of these interface lists are a really powerful way of grouping a specific type of interfaces together. Well, this has now been brought to CAPsMAN, and in the CLI, it's not in Winbox yet, but in the CLI, we can actually now specify an access list in the, an interface list in the access list. And the other thing is to do with interface lists is in the data path settings, that when a interface becomes active and comes alive because of you provisioning it and because it has had the settings applied to it, and it comes up and it comes alive and it's communicating with CAPsMAN, it will pop that interface into an access list if you've defined it in the data path. That has now appeared in Winbox. It's right at the very bottom of the data path config, but you need the latest RC version for these. But now in Winbox, you've now got a drop down at the bottom and you can choose which interface list you would like that data path to put those CAP interfaces into. Thank you very much, gentlemen and ladies.